your highest block. Naturally, your highest block, no matter looking at how solid it is, you look at an ice block, the temperature equivalent of an ice block, let's say minus 20 degrees Celsius. Do you understand? So if this ice block is now said to what? Melt. If this ice block is being subjected to heat by melting it, now there is a particular region it gets to. Instead of the temperature to be dropping, instead of it to be what? Contracting. When I say contracting, when it's subjected to heat, it's now being what? Expanding. It's now expanding. It's an ice block, fine. But naturally, it is to be the block. When heat is subjected to heat, it's supposed to be what? Melting, and to be turning to liquid. But a particular time came, instead of it to what? To melt, that is expand, it was what? Contracting. When it's melting, it's what? Expanding. Do you understand? The structure is expanding. But a particular region of temperature will come where instead of it to be what? Expanding, it's now be contracting back. Now we look at it very well in a clear term. First of all, let's look at the actual meaning of anomalous expansion of water. In simply a situation when water at minus 10 degrees Celsius, this is the statement 2, is heated and expands slightly until from minus 10, from minus 10 to minus 5, minus 3, minus 2, until it gets to 0 degrees Celsius. It expands slightly until it gets to 0 degrees Celsius. Thereby, it melts into water at that same 0 degrees Celsius. Now, it melts into water at the same temperature and begins to contract instead of expanding. If this is the rate of, let's say this is expansion rate now, and this is temperature. If that water is, let's say, as temperature is, let me put temperature here for understanding. This temperature, and this is our expansion rate. Do you understand? As temperature, the temperature is, let's say, this is 0, this is 90, this is 80. Now, if at minus 10 degrees Celsius, naturally, it's supposed to be expanding. It's supposed to be going up as in continuing. As this temperature is what? As this temperature is increasing, do you understand? From minus 10 to minus 5 to minus 3, 0, like that. Then 10 upward. Now it's supposed to be expanding. Now a situation whereby it now contracted before it expands again. At that region where it came to what? Contract. Do you understand? Before expanding again. That single point is what we call anomalosity or anomalous expansion. Do you understand? Anomalous expansion of water. That is wrongful behavior. Naturally, it's not supposed to what? Contract. It's supposed to continue to what? Expand. They said it melts into water at the same temperature and begin to contract between 0 degree to 4 degree. At that point, anomalous. So it means that if you are explaining, if you are being questioned or being quizzed that explain anomalous expansion of water, you just say it's a situation whereby when water is at 0 degrees Celsius and being subjected to heat, it tends to expand continuously until 0 degree. Now, from 0 degree to 4 degrees Celsius, it contracted. It did not expand. It contracted before expanding again. So at that region, anomalous expansion had occurred. Look at this is another graph showing your volume, and your what? Degree temperature. You understand? Now, this is the volume. At this region, the volume is dropping. Drop to, at that point of 0 degrees Celsius. Do you understand? At that point of 4 degrees Celsius, this is, let's say, 100. At that point to 0 degrees Celsius, it started from here. At that point, instead of it to what? Expand. This is the region of, this is expansion. Expansion, as in the volume is higher. Now, when it contracted, the volume will go low. Do you understand? Contracted at this 0 degrees Celsius to 4 degrees before it now what? Expanded again. So that is just the explanation of what? Anomalosity of water. Once again, I said from 10 down to 0. What is it doing? It's expanding. But from 0 to 4, it contracted. So from 4 upward, it begins to expand again. So that particular region of what? Contraction of water between 0 degree to 4 degree is what we call anomalous expansion of water. So at this junction, we'll go into some work examples. Of what? Our linear expansivity and all other things we discussed. Number 1, question 1. Let's deal with question 1 without wasting much of time. Number 1 says, calculate the linear expansivity alpha of a brass. Write out your parameters. That's instruction. Always exercise. Always write out your what? Parameters. Initial length is 120. That assumes a new length. That's your L2. 120.05 meter. That's the L2. When heated all through, so it means that your initial length L2 minus L1 is what? 100 degrees Celsius. Heated all through. That is, the initial final length is what? Final length is what? 100 degrees Celsius. Your initial length. Let's say 0 degrees Celsius. Heated all through. Now, they now said, hey, what are you looking for? Linear expansivity. So, formula for linear expansivity is given as L2 minus L1 over L1 into bracket theta 2 minus theta 1. Are you seeing that? So from here, L1 is 0. So, L1 is 120. L2 120.02 minus L1 120 all over L1 is 120 into bracket L2 is 100 minus 0. So from here, you're going to get your alpha to be 120 minus this, you have your 0.05 all over 120 times 100. Do you understand? So remember, the SI unit is what? Per Kelvin. So from here, you say your alpha equals 0.05 all over 1200. That's what? 12,000. So if you use matrices here, you use your indices here, you have 5 exponential minus 2, then you have 12 exponential 3. So if your 10 comes up, you have alpha equals 5 times 10 is to the power minus 2 times minus 3 all over 12. So from here, you have 5 here 1. Let's say 5 divided by 12. You have something like this, 0.12 here, you have 3. You have 4. So put your 4 here, when you multiply, you have 48, subtract 2. So by the time you bring you still have 1, let's use this 0.41. So your 0.41, you understand, times your 10. These two, by the time you solve it, this minus becomes minus 5. So if you continue, you have 4.1 times 10 is to the power minus 6. That will be your answer. Our question 2 says, in which of the following is the molecule of water moving faster? Probably when heated. In which of the following is the molecule of water moves faster? A, we're given steam. B, we're given ice. C, we're given ice water. That is a water that is just iced. It has not what? Become solid. Then D, we're given normal water. If you analyze it based on our fundamental knowledge of movement of what? Atomic structure. For steam, there is higher rate of what? Atoms of molecules. Atoms of what? Molecules. Why? Because it has a free movement of what? Atoms. Due to the fact that the what? The intermolecular forces are what? 0. They are not strong. But for ice, this one can't even be, because the whole intermolecular forces are strong by what? Are bound by what? Strong what? Intermolecular forces. Iced water, almost the same as what? Ice, because it's heading towards ice. Water is still manageable, but the best answer here is our steam. It has the highest what? Movement of what? Water molecules. Now, the third question says that using the calculated question above from question 1, determine the increase in volume of a brass container. with the original volume equals to 100 meter, if heated through a temperature of what? 50 degrees Celsius. Now, how do you calculate it? They say calculate above, determine the increase in what? Volume of a brass. The increase in volume, what do we do? What do we do? Our gamma is what? Our gamma is what? Our gamma is V2 minus V1 all over V1, then change the what? Temperature. Right? Now, they said from the question above. Now, in our above question, we already got our alpha. Our alpha is 4.1 times 10 to the power minus 6 per Kelvin. And we said the relationship between alpha and gamma is that gamma is 3 times alpha. Right? Now, if gamma is 3 times alpha, it means that our answer times 3 will give us what? Our gamma, which is our what? Volumetric expansion. So this is times 10 to the power 6 per Kelvin. So from here, I'm going to have 12.1 times 10 to the power minus 6, 12.1, 12.3 per Kelvin. So this is our what? Gamma. So if we now told to calculate that, our what? Change in temperature. Theta 2 is 50 degrees Celsius. From the analysis, theta 1 is still 0. And